Hello, everybody. So today we are starting section 3.6 notes, theorems about roots of polynomial equations. So today's objective, by the end of class, you should be able to solve a polynomial equation. So as a warm-up, let's solve some polynomial equations we have familiarity with. So go ahead and do examples 1, 2, and 3. At this point, please pause the video. Once you've finished the warm-up, please resume. All right, let's see how we did. So for number 1, that quadratic was factorable. So we get x equals 5 halves and x equals 1. For number 2, that quadratic was not factorable, so I chose to use quadratic formula to solve since our a value was not equal to 1 and our b value was not even. Now number 3, that is a cubic polynomial, 4 terms. Tried to factor by grouping, tried rearranging. No matter what, this didn't factor by grouping. I couldn't get that common factor. So how the heck do you solve a polynomial when it doesn't factor? Or it's not a quadratic and you can't do the quadratic formula? Well, that's what we're going to talk about today. So, as we saw in examples 1 and 2, solving for the zeros of a polynomial is easy when a polynomial is factorable, or when you know where to start. But how do you solve a polynomial when there's nowhere to start? Well, sometimes we can pull information from a graph. So for example, h of x equals x to the 5th minus 8x to the 4th plus 13x to the 3rd minus 56x squared minus 300x plus 3,600. We're going to factor this completely, and we are going to find all real and complex zeros of the polynomial function. So below is the graph of h of x. So right away from this graph, I'm able to pull some information. I know that x equals 6 is a root of this polynomial with a multiplicity of 2. And I know that x equals -4 is a root of this polynomial with a multiplicity of 1. So right away, I know that h of x has a factor of x minus 6, since x equals 6 is a root, and that is a factor twice, since the multiplicity of that root is 2. I also know x minus 4 is a root of the polynomial, which tells me x plus 4 is a factor of this polynomial with a multiplicity of 1, so it's just a factor once. Problem is, h of x is a degree 5 polynomial. Right now, if I were to distribute out these 3 factors I have, I'll get a cubic polynomial. So I know I'm missing a degree 2 polynomial here. Maybe 2 linear polynomials or maybe a single quadratic polynomial, but I know that I'm missing some factors. So we have to find the other factors. Well, since I already know 3 roots of this polynomial, I can use what we learned in class on Tuesday and start dividing by the factors I know to get down to hopefully a polynomial I can then factor and solve to find the remaining roots and remaining factors. So let's start with our first root. We know that x equals 6. So I am going to, since x equals 6 comes from the factor x minus 6, I can use synthetic division. So I'm going to divide the polynomial by x minus 6, but using synthetic division. So I put 6 on the outside. Underneath, I have the coefficients of h of x. So that's 1x to the 5th minus 8x to the 4th plus 13x to the 3rd minus 56x to the 2nd minus 300x plus 3,600. I don't need any zeros for placeholders because I have the coefficients of 5, 4, 3, 2, 1, and 0. So I drop down, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add, and we get remainder 0, which we should get because we know x minus 6 is a factor of h of x. So it should go in evenly when we divide by it. So now I can divide again by 6 since the multiplicity of this root is 2. Drop that first number down, multiply, add, multiply, add, multiply, add, multiply, add, and again we got remainder of 0, which we knew we should have gotten since x minus 6 was a factor twice. And now I've used up that multiplicity of 2, so I have to move on to my other root, x equals -4, my other factor, x plus 4. So I divide by that, drop down, multiply, add, multiply, add, multiply. Awesome. So I started out with a degree 5 polynomial, and I divided by 3 linear factors. So degree 5 divided by x minus 6 got degree 4, divided by x minus 6 got degree 3, divided by x plus 4 got degree 2. So my remaining polynomial factor is x squared plus 25. If x squared plus 25 were to factor further, we would then factor that polynomial. However, x squared plus 25 does not factor to have real factors. It would have complex roots. So this is completely factored. That was part A, factor h of x. Check, we did that. Now, what are all the real and complex zeros? So I know 6 is a 0 with multiplicity of 2, -4 is a 0, and then x squared plus 25. Let's solve for those zeros. Subtract 25, take the square root, and we get plus or minus 5i. Because the square root of -25 is imaginary. And there we go. We just solved that polynomial and factored that polynomial. Very impressive. So how do we go about solving if I don't have somewhere to start, if I don't have a graphing calculator where I can graph and find a root on my graph, or maybe all of my roots, aren't nice integer values? Well, we do have some help. We have a theorem called the rational root theorem. So the rational root theorem gives a list of possible rational roots and zeros of a polynomial function. Not every number on the list will be a 0 of the function, and not every rational 0 of the polynomial function will appear somewhere in the list. I'm sorry, I completely said that wrong. Not every number on the list will be a 0, but every rational 0 will appear somewhere on the list. So I think of it like a word bank. If you have an answer, it's coming from this word bank. Now, you might not use every single word, but if there is an answer, it's coming from that word bank. That's how I think of the rational root theorem. Not all of them are actual roots, but if your polynomial has a rational root, it is one of the ones listed. So how do you find that list? Well, if polynomial p of x has integer coefficients, then every rational root of the polynomial equation p of x equals 0 can be written in the form p over q, where p is a factor of the constant and q is a factor of the leading coefficient. So let's take another look at problem number 3 from our warm-up. Find all real and complex roots of the polynomial equation x to the third plus x squared minus 3x minus 6 equals 0. Let's start with our rational root theorem, and let's find all possible rational roots. So, rational root theorem says that if we have any rational roots, they'll be able to form p over q, where p are the factors of our constant. So the factors of 6 are positive and negative 1, positive and negative 2, positive and negative 3, positive and negative 4, 6. Nope, not 4. I just started counting. 1, 2, 3, and 6. Our factors of q are the factors of the leading coefficient. So our factors of 1 are just positive, negative 1. So the rational root theorem says any rational root will be of the form p divided by q. So if I take p divided by q, 1 divided by 1 gives me 1. 2 divided by 1 gives me 2. 3 divided by 1 gives me 3. And 6 divided by 1 gives me 6. So I have 8 possible zeros here. Positive 1, positive 2, positive 3, positive 6, or negative 1, negative 2, negative 3, negative 6. So how do I determine which one of these possible rational roots are actual rational roots, right? This is my word bank. Now, which one of these are actually the answers? So if you have a calculator, easy peasy, graph it and look, just like we did in the first example. However, what if this is on a non-calculator? So if this ends up being on a non-calculator, the only way that we can check to see if these are actual roots is guess and check, synthetic division, see if the remainder is 0. So let's start that. Practice for the worst case scenario. So I'm just going to go in order. I'm going to start with positive 1. So let's go ahead and divide x to the third plus x minus 3x minus 6 by positive 1. I divide by positive 1, and I do not get a remainder of 0. I get a remainder of negative 7. So that means that x equals 1 is not a root of our polynomial. So let's try again. Let's go ahead and divide by negative 1. If you want to pause for a second and divide, and then resume once you're done. Otherwise, I'm about to show in 3, 2, 1. All right, we divide by negative 1, and wow, we're unlucky again. I divide by negative 1, and I have a remainder of negative 3. So both positive and negative 1 are not actual roots. All right, maybe we'll get lucky with 2. Let's go ahead and divide by 2. So again, if you'd like to pause and resume once you're done, I'm going to show in 3, 2, 1. Woohoo! We found it. So x equals 2 is a 0 with at least multiplicity 1, maybe 2. I could try again, but we found 1. That's all we need, which means we know x minus 2 is a factor of our polynomial. All right. So let's solve completely over the real and complex number system. So now that I know that x equals 2, I divided by x minus 2, and I was left with the quadratic x squared plus 3x plus 3. This quadratic is not factorable. It'd be wonderful if it was, but it's not. So I have to solve for the remaining roots I'm going to use a quadratic formula because my b value is not even. So x equals opposite b plus or minus square root of b squared minus 4ac all over 2a, which gives us -3 plus or minus the square root of 9 minus 12 all over 2. Which then gives us -3 plus or minus the square root of -3 all over 2, which then gives us -3 plus or minus I root 3 all over 2. I'm going to clean this up really quickly so I don't have the double writing. There we go. All right, so solved completely. We got -3 plus or minus I root 3 over 2 from that quadratic, but don't forget that original 0 we found using synthetic division. So I was not able to see these two complex solutions using the rational root theorem because complex numbers are not rational numbers, but I was able to initially find that 2 to get us started. All right, so let's use the rational root theorem to list all possible rational roots of each polynomial function. So for examples 2 and 3, we're not solving. We're just doing what we did here in step 1. We're listing all possible roots using the rational root theorem. So go ahead and do example 2 and example 3 on your own. I'm going to pause, sorry, I'm not going to. You're going to pause the video. When you're finished with example 2 and example 3, resume the video because I'm going to show the answers in 5, 4, 3, 2, 1. All right, hopefully we did well. So for number 2, P are the factors of the constant, so the factors of 9 are 1, 3, and 9. Q are the factors of the leading coefficients, so our factors of 1, 2, 4, or of 4 are 1, 2, 4. So P divided by Q, 9 divided by 1, 3 divided by 1, 1 divided by 1, then 9 divided by 2, 3 divided by 2, 1 divided by 2, then 9 divided by 4, 3 divided by 4, 1 divided by 4. So we had lots of options there for number 2. Number 3, P are the factors of 51, so that's 1, 3, 17, and 51. Q are the factors of 1. Great when that happens, because then I only have one divisor. So we end up getting the possible rational roots are positive, -1, 3, 17, and 51. Hope that went well. So to wrap up today's lesson, let's use examples 2 and 3, the 2 that we just did, where we found all possible rational roots, to solve for all real and complex roots of the polynomial. Now, I'm not going to make you guess and check using synthetic division this time. If you would like to use your graphing calculator, now that we have the possible rational roots, if you'd like to use your graphing calculator, enter this into your y equals and graph and take a look and find the rational roots that way, like we did in the first example today with the graph, go ahead. So please do 4a, which is example 2 from the practice. 4x to the third minus x squared plus 36x minus 9. Go ahead and solve this polynomial. Pause the video and resume in, because I'm going to show the answer in 5, 4, 3, 2, 1. All right, so this was factorable. You didn't have to use rational root theorem, graph it, or anything. We could completely solve this one just by factoring. We grouped the first 2 terms together, and we get 4x minus 1 times x squared plus 9. Split up those factors, set each one equal to 0, and we get x equals 1/4 and plus or minus 3i. All right, hopefully that went well. Go ahead and try B. Again, B is example 3 from the previous page. X to the third plus x squared minus 11x plus 51. You're welcome again to type that into your y equals and graph it and take a look at the graph to find a 0, unless it's factorable. So please pause your video because I'm going to show the answer in 5, 4, 3, 2, 1. So this one was not factorable. So when I graphed, I was able to see that -3 was 0 of this polynomial, meaning x plus 3 is a factor. So I use synthetic division to divide by x plus 3, and I'm left with the quadratic x squared minus 2x plus 17. Since b is even, I decided to solve this one using completing the square. So I moved 17 over to the other side, added 1, so the left side factored to be x minus 1. That kind of looks like an I. That's a 1. Squared equals -16. So square root of both sides, square root of -16 is plus or minus 4i. Add the 1 over, so we get 1 plus or minus 4i. And then don't forget the original root that we found using the calculator, -3. All right, I hope that today's lesson went well. If you struggle at all with today's lesson, we are continuing on with it on Monday, but also please feel free to come see me during my office hours or stop in the Math Resource Center. Have a great weekend, everybody. Your homework is in your homework packet, and I will see you all on Monday. Bye.